Hello, my name is Ashkbiz Danehkar. I'm a research scientist at Eureka Scientifics, and today I will talk about my work on the condition for cool superwind in massive subforming regions. And I recently did some work in collaboration with Salio and Will Gay on the radiative cooling of the superwinds. And this is the outline of my talks. I will talk about the Superwind and Superbubble and the formation of radiative coolings and how I implemented hydrodynamic simulation of superwinds and photoionization modeling of these superwind results. Typically in self-forming regions we see the formation of superwind, and we also in X-ray observation we also see large-scale superbubble. However, radio and ALMA observations suggested the formation of cool superwinds. Here you see the schematic view of superwinds. On the left you see a region with formation of superbubble, and on right we see, because of cooling, the bubble broken. And there is some theoretical work by Javier Kelage in which they assume adiabatic fluid model. In these solutions we see the density and temperature are as a function of radius, and they decline by power of -2 and power of -4/3 respectively. And however, there is a semi-analytic study by Silich in which they couple radiative cooling functions to fluid model, and here on right you see departure from adiabatic solutions because of radiative coolings. And here we see four different wind region which defined by Weber in 1977, and we have the region of free expanding wind regions and formation of hot bubble in temperature profile and formation of shell in density profile, and then followed by ambient medium. In order to implement hydrodynamic simulations of subdisturbed winds, we set some boundary conditions and some initial conditions, and I use the package Mayhem which built on the Flash hydrodynamics codes. And in this package the radiative cooling function and photoheating function coupled to the fluid equations. I use SRS 99 to make SED profiles and use this SED profile as input for or hydrodynamic simulation, also or photoionization modelings. And here you see the fluid equation which we solve using Mayhems, and the radiative cooling functions calculated using cooling efficiency, and photoheating function also obtained using heating efficiency, which made by photoionization cross sections and SED profile. And here you see the result, hydrodynamic simulation. On right we see 1D profile, and on the wind with low velocity 250 we see a departure from adiabatic solutions. On dashed line adiabatic solutions, and solid line is those with predicted by our hydrodynamic simulations. And this departure depends, as you see, on terminal wind velocity. And here you see 2D simulations which show formation larger scale superbubble in temperature and density profile. And based on departure of density profile from adiabatic solution, we classify wind under adiabatic bubble and catastrophic cooling with bubble, and catastrophic cooling without bubble, CB and CEC. And using that criteria we classify different wind region in parameter space of mass loading rate, wind thermal velocity, and metallicity, ambient density. And here we see by increasing metallicity, we increase radiative cooling, and also by decreasing wind terminal velocity, we also increase the radiative coolings. And here there is a wider parameter range, which we have change of mass loading rate. As you see, by increasing the mass loading rate, the chance of radiative cooling increase. So we have higher radiative cooling when we have higher mass loading rate. And here there is a parameter range on the right bottom. MC is momentum conserving winds, which we have momentum driven outflow, and is formed by very strong radiative cooling, and the formation of bubble and shell totally suppressed. However, we have different H2 regions, and the thing which I consider in previous model was typical H2 regions, which has cluster radius 1 parsec, ambient density of less than 10,000 invert cubic centimeter, and for outer compacts we have much higher ambient density, 10 to the power 4 invert cubic centimeter, and much smaller cluster radius, 0.01 parsec. And I also run hydrodynamic simulation for the parameter which suitable for outer compact H2 regions. And here we see by decreasing cluster radius, we also increase radiative cooling. So in the region which parameter which have adiabatic solution, if we reduce cluster radius, we also have CB catastrophic cooling with bubble and CC catastrophic coolings. Also there we see dependence on density, ambient density. By increasing ambient density, because the ambient pressure is increased, we also reduce the chance of catastrophic cooling because of ambient pressure. I use the result of hydrodynamic simulation, density and temperature profile, which predicted by our hydrodynamic simulation, and use this temperature profile as an input to photoionization calculation by Cloudy. And using this calculation, I made collision ionization combined with photoionizations. On top we see the model pure photoionization without any thermal effect from hydrodynamics, and on bottom we see CPI. CPI is collision ionization plus photoionization, and because of temperature profile which made by hydrodynamic simulation, we have different departure from pure photoionization. In the bubble we see here the formation of oxygen 6, which we don't see in pure photoionizations. And other thing I did is a time-dependent photoionization calculation, which I did using the Mayhem. Non-equilibrium ionization typically happen in the region where the time scale of collision ionization is much longer of time scale of radiative cooling. So radiative cooling is very fast. And here is in this plot you see in the carbon 4 and carbon 5, and also oxygen 6 and oxygen 7, and we see departure from collision ionization, and this is the region below 10 to the power 6 where the non-equilibrium ionization happens. And here we see the result for pure photoionization, collision ionization plus photoionization, and non-equilibrium photoionization at the bottoms. So we see enhancement of carbon 4 in the region of free expanding winds, and this is because of time dependence calculations. And the other thing is we did this emissivity and by integration we calculated line luminosity, which is comparable to observed flux. And for more result, you can look at my poster in Focus Meetings 4. And here I made UV diagnostic diagrams, and as you see in this plot, the shady light color are for collisionization and solid color for non-Coulomb photoionization. Here you see for high metallicity we have enhancement of carbon 4, and for low metallicity we also see enhancement of oxygen 6. And other thing is my future plans. I plan to incorporate radiative transfer units, because mayhem calculation done using a simple power law radial assumptions. Here you see 2 power of minus 2, and there is now detailed calculation of optical dips, and detailed calculation of this can done using the radiative transfer units. And when we include radiative transfer unit, we have radiative pressure, which lead to radiative derivatives, also outflow. And in this link you can look at our hydrodynamic simulation result and animations. And this is summary of my talks. I talked about how I implement hydrodynamic simulations and how I calculated collision ionization and non-local ionizations, and I present some result on wind region of ultra-compact H2 region, which is the paper in preparations. And in ultra-compact H2 region, the ambient density is higher than typical H2 region, and cluster radius is smaller than typical cluster in H2 regions. So if you have any question, you can ask me in a Slack channel, so I will be happy to answer. Thank you for your attention.